So what I want to do in this video is I want to take a look at the energy diagrams for the various pi systems from 2 pi orbitals up to 6 pi orbitals. So we want to look at epi. There's T2H4. We want to look at the allylic system. And it doesn't really matter whether we look at the carbocation, the radical, or the carbanion because the orbitals are the same. So this is the allyl radical. And we want to look at the butadiene. And then we want to look at the pentadienyl system. And then we want to look at 135 hexatriene. So the number of pi orbitals goes from 2 pi orbitals to 3 pi orbitals. And we know that when there are an odd number of pi orbitals, we will actually have a non-bonding orbital. 4 pi orbitals, 5 pi orbitals. And again, we know that since it's an odd numbered system, there will be a non-bonding orbital that's at the same energy as the original p energy levels to 6 pi orbitals. And we know that the even numbered systems will not have any non-bonding orbitals. There will be an equal number of orbitals below and above in all of these cases, but since there are a total of odd number of orbitals there, in order to have an equal number of orbitals below and above, the center one has to be at the original p orbital energy level. So what we want to do is we want to kind of put our p orbital energy level down the center. Actually, I think I'm going to do this over here so I have the entire board. I'll put my p orbital energy level down to the center. Energy on the vertical axis. And we know that the 6 pi orbital system had approximately equally spaced orbitals. So hopefully I've drawn that approximately to scale so that the gap between these orbitals is about the same for each set. The 5 pi orbital system will have pi 3 non-bonding here and approximately evenly spaced orbitals. That, and I'm probably exaggerating a little bit. That's intentional. So there's the butadiene, there's 2 orbitals below and 2 orbitals above. Alkyl system, and then if we look at a beam should look like that. So we're looking at our 2 pi orbital, our 3 pi orbital, our 4, etc. And what you'll notice is a steady decrease in the energy of pi 1. As we increase the number of atoms, carbon atoms, over which the electrons can spread, they get more stable. They're attracted to a larger number of nuclei. They're happier. You'll notice a steady increase in the energy of the highest energy orbital. In fact, the same amount of increase as we extend the system as the lowest energy orbital decrease. That doesn't matter, because we're leaving that orbital empty. So it has no bearing on the stability of the system. The stability of the system is controlled by the net drop in energy of all of the electrons versus where they started. So these electrons drop the most. These are the ones that are most concerned with affecting the stability of the system. As you go from the 2 pi electron system to the 4 pi electron system, what I think you'll notice, assuming I on this properly to scale, is you'll notice that pi 2 is higher in energy than pi 1. So as we extend the system, the HOMO gets closer to the p orbital energy level. That increased energy of the HOMO causes the reactivity to increase. Where the decreased energy of the lowest energy orbital causes the stability of the system. These 2 orbital electrons are slightly less happy than they would be if we just had 2 isolated pi bonds and they weren't interacting at all. But these 2 electrons are substantially happier. These have dropped more relative to where this HOMO energy was than these have risen. So if you take the 4 electrons in total in the diene system, they're happier in the conjugated system than they would be in 2 isolated bonds where you just had another pi 1 and pi 2 identical in energy to this pi 1 and pi 2. And I haven't done a very good job at drawing this to scale because this pi 3 should be higher in energy and therefore closer to the orbital energy level than the other orbitals. So I'm going to have to redraw those to get them closer to where they really should be. Should still be seeing this drop. It's dropping less quickly as we go. So the HOMO orbital gradually rises in energy as we extend from the 2 carbon to the 4 carbon to the 6 carbon, which causes it to continuously increase in reactivity, while the low energy stable orbital continuously drops. What we'll find, though, is that the number of orbitals increases more rapidly than the gap between the highest and lowest energy orbital and the effect of that is that the orbitals get closer together for the longer system. So that delta E decreases as the system gets longer. And because that delta E is inversely proportional to the wavelength of light, the wavelength increases as the system gets longer. If we look at the UV absorption, for Fe, it's approximately 171 nanometers. And if we were to look at 1,4-pentadiene, it's not much different at 178 nanometers. Each of these pi bonds is roughly not interacting with the others. If we look at the 1,3-butadiene, though, that goes up to 217 nanometers. And if we look at 1,3,5-hexatriene, that goes up to 268 nanometers. And these are all still in the ultraviolet, the violet visible range beginning at about 400. And if we look at the corresponding tetragene, that has gone up still further to about 330 nanometers. So this is 1, 3, 5, 7 octa tetragene. And that goes up. If we put methyl groups on the system, extra CH3 here, that changes it a little bit. Goes up to 222.5. And if we were to put methyl groups on the ends, so we have 4 CH3 groups on the ends of the system, that raises it to 241.5. And still UV. Right? We're still not in the visible range. So what you'll notice is that extending the conjugation by an additional double bond seems to raise it by somewhere between 40 and 50. In this case, the difference between 171 and 217 is about 46. The difference between 217 and 268 is 51. And the difference between 268 and 330 is 52. So it seems to go up by about 50. A little bit more as you increase the system. But we can round these and say that each time we increase the length of the conjugated system, by 2 carbons, lambda goes up by around 50. We don't need to know the exact number. Don't bother memorizing these numbers, it's not worth it. The other thing we'll notice is that we increase the number of hyperconjugations, right? 217 to 222.5, that difference is approximately 5, right? 5.5. If we have 4 hyperconjugation interactions, we've gone up from 217 to 240. That difference is around 20-ish. All right, so 24.5. Here we have 1 hyperconjugation interaction. Here we have 4. We can approximate, we can say that each additional hyperconjugation anytime with an additional alkyl group bond lambda increases by approximately 5 nanometers. Those are very rough approximations, but they are kind of borne out by the observed data. Extending the conjugated pi system by an additional pi bond, by adding 2 carbons, raises lambda by about 50 nanometers, and putting additional alkyl group. Hyperconjugation is a pi orbital phenomenon, just like conjugation, because it's sigma electrons from an adjacent carbon-hydrogen or carbon-carbon bond donating into the pi system to stabilize the pi system. So that's a less, that's a smaller effect, right? Because these electrons are not actually becoming part of the pi system per se. They're already involved in a sigma bond to one of the adjacent atoms. So they're only donating a little bit of themselves into the pi system. So we're increasing the number of pi symmetry orbitals when we do hyperconjugation. We haven't attempted to show that because it becomes complicated when you have to consider the sigma electron framework in a molecular orbital theory diagram. But we're increasing the number of pi orbitals, but we're not having as much an effect on the lower energy pi orbital when we have this sigma electron system donating into the pi extension, the extended pi system, as when we're actually extending the pi system completely. So these are numbers that are worth remembering. It's worth remembering that it starts out at about 170 nanometers for just an ordinary carbon-carbon pi bond. And then it's worth remembering that each additional alkyl group that introduces hyperconjugation raises the wavelength by about 5 nanometer, and each additional pi bond that goes into conjugation raises it by about 50. That'll give you a rough approximation, and will allow you to determine that if you see a wavelength of about 330, you can subtract 170 from that. And by looking at that difference, in this case, 160, divide that by 50, that's approximately equal to 3. That's consistent with adding 3 additional pi bonds. There are some much more elaborate rules for determining the likely wavelength of absorption, and they were developed by a man named Cotton. So they're called Cotton's rules, and he developed them when he was studying steroids. And they work very well for steroids and somewhat less well for non-steroidal molecules. Something else which is worth knowing about these extended systems is that if you just have plain 1,3-butadiene, we saw that at 217 nanometers. If you lock this in a ring, however, so you have 1,3-cyclopentadiene, because there's an sp3 hybridized carbon in here, this isn't a cyclic pi system, it's still the 4 of the pi system. That wavelength goes up to about 239 nanometers. And if you lock it into a 6-member ring, 1,3-cyclohexadiene, goes up to about 259 nanometers. So it's going up by about 20 nanometers in each case. And what you're seeing is greater rigidity forcing the pi system to be more planar. There is free rotation about this carbon-carbon bond. Well, relatively free rotation. As it turns out, the energy gap between this, which is referred to as the S-trans, where the two double bonds are on opposite sides of that sigma bond, versus this S-cis isomer, the energy difference between these two is about 3 kilocalories per mole. And the barrier for rotation is significant because you have to actually break the extended pi system in order to rotate about that bond. But we have the ability to rotate around that bond. And when the 2 pi bonds are not coplanar, we don't have the benefit of the extended pi system. Here, where we have sp2 hybrid carbons in a regular hexagon, and in a regular hexagon, 120-degree bond angles are the ideal, we force the system to be more nearly completely planar, and we increase the benefit of conjugation. We move those orbitals a little closer to each other, and we get a slightly higher wavelength of absorption. You might predict that if you trap these into a 4-membered ring where there's a lot of ring strain, right, that you're not going to get as much benefit from the pi system, that you're going to have a more energetic system than you would expect just from the wavelength. It might even be on the other side of 217. So that's something to know, that as you increase the ring size, at least from the acyclic system to the 5-membered ring to the 6-membered ring, you go up by about 20 nanometers. The other thing that's interesting is to think about carbon-oxygen pi bonds as opposed to carbon-carbon pi bonds. There are actually 2 wavelength absorptions for this system. And they're at about 190 nanometers and about 280, I think it is. This one is what we refer to as a pi to pi star transition. And this one is what we refer to as an N to pi star transition. because there are lone pairs here, these are non-bonding electrons, we have the possibility of electrons being promoted from the pi to the pi star orbital. With this energy gap. But we also have the possibility of electrons being promoted from the end to the pi star orbital with a different energy gap. The non-bonding orbital is higher in energy than the pi bonding orbital, so this delta E is always smaller. Which means that there's going to be a larger wavelength. This is a larger delta E, thus a smaller wavelength. The other thing you'll notice in the UV spectra of the carbon-oxygen pi bonds is this is very intense heat with a high molar radioactivity. Whereas the N pi star is a weak absorption. With a low molar activity. And that's seen in what we refer to as the molar activity or the extinction coefficient, which is an epsilon. Because it's the extinction coefficient in the old literature. It's the same thing as molar activity. And epsilon is for the 280 nanometer one, I think approximately 15. Whereas for the 190 nanometer, it's on the order of about 10 to the fourth. So a photon that has the right energy to promote an electron from the pi orbital to the pi star orbital does so a much larger percentage of the time than a photon that has the right energy to promote an electron from the non-bonding orbital to the pi star orbital does. That's because it actually violates principles of symmetry. It's not possible to promote an electron from an orbital of one symmetry to an orbital of a different symmetry. The pi and the pi star orbital have the same symmetry, so that is symmetry allowed. This is symmetry forbidden. So in theory, it shouldn't be possible for it to happen at all. In practice, a small subset of photons break the rules and say, I don't care that it's symmetry forbidden. Here I have the right energy. Electron take the energy. You're going up into the pi star orbital. Deal with the symmetry change. But it takes some convincing to get the electron to agree to that change in symmetry. Most of the time, the electron sees that photon, sees that it has the right energy to promote it to the pi star. He said, no, I'm not allowed in that pi star orbital. I've got symmetry in plane, so I'm just going to turn that photon down and not take it. So the pi to pi star transition is always more intense than the n to pi star transition. You don't have n to pi star transitions in the hydrocarbon systems because carbon is halfway across the p block, which means it has 4 electrons, albeit 8 possible. And hydrogen is halfway across that s block, which means it has 1 of the 2 possible electrons. So there are no lone electrons in the hydrocarbon system. But as soon as you put a heteroatom, an oxygen or nitrogen in there, that's further than halfway across the p block, you have unpaired electrons, in a lone pair, you have a non-bonding pi orbital that contains those electrons, and you start to see this N to pi star transition. So you'll actually see a UV spectrum that looks like that. It has a low intensity N to pi star at a higher wavelength than the pi to pi star. The N to pi star transition is closer to the visible range, so we don't have to extend the pi system by as much when we have a carbon oxygen double bond as part of that pi system in order to get into visible range. And you start to see color in aldehydes and ketones before you start to see color in the ordinary saturated hydrocarbons, or in this case, unsaturated hydrocarbons. So you should remember that kind of acetone, I think it's acetone actually that has the 190. You should remember that acetone is about 190. That's about 20 higher than the ordinary ethene, the carbon-carbon pi bond. And there's another one, it's roughly 100 higher-ish. That's the N to pi star transition. So if you were to extend the conjugation and put another pi bond in here, you might predict, because we know that extending by a carbon-carbon pi bond tends to increase the wavelength by about 50, you might predict, yeah, it's going to be somewhere around 330. That's about the same place as you would see the pi to pi star transition for a tetrahedron. But that N to pi star transition is the one that's going to get you colored too. So we're not going to do a lot with UV spectroscopy. It's not useful at all, except in organic chemistry, except for measuring the approximate length of an extended pi system.